levitating pencil activities to allow students to experience the basics of magnetic levitation. This is technology that has been used for maglev trains that have been running in China for many years. Their speed is 430 kilometers an hour. In another session, we talked about quantum spin and explained that magnets are made by aligning the quantum spins of vast numbers of electrons in special materials. Both of the activities in this video are about using quantum spin. Let's start the activity. In the first activity, we are using lots of little ferrite magnets that can be bought at hardware shops. They have a central hole. Let's first make a magnetic spring to understand north and south poles. The magnetic spring is a maglev experiment. I will now demonstrate how to make the pencils levitate. For this activity, children need 6 magnets each, stiff packing foam, a sharp paper cutting blade to make slits in the foam, and a flat piece of plastic to be an end support. Make sure magnets fit a bit tightly onto the pencil. Use a bit of tape or glad wrap if the magnets are too loose. This will only work with one configuration of magnets. You need to feel the forces to make sure that it will repel. To be stable, the magnets on the pencil must be in exactly the right place. Now that you have levitation, it is time to see how well it works. Students should be able to spin the pencil and see how long it spins. You could have a competition to see whose pencil stops last, measuring the time with a stopwatch. We have another fancy spinning pencil equipment that you can buy online. This one spins in the sun. If you want to lift very heavy weights like a train, you need really strong magnets. The world's strongest magnets are made by superconductors. These are special materials that conduct electricity with zero resistance, so electric currents can flow forever. Up to now, superconductors only work when they are very cold. There is a huge worldwide race to create superconductors that work at room temperature. No one has succeeded yet. Now I'm going to show you magnetic levitation using superconductors cooled with liquid nitrogen. Superconductors work by making electrons move in pairs. They are called Cooper pairs. How they work is all about quantum spin. If you did our quantum spin activities, you would know that electrons have a quantum spin of a half. We learnt that quantum spins can add up or cancel out. When we line up all the atoms so the electron spins are aligned and add up, we have a magnet. 2 electrons in a Cooper pair have their spins aligned, or much more commonly anti-aligned, so one points up and the other points down. So the total quantum spin can be a half plus a half equals 1, or a half minus a half equals 0. That means that a pair of electrons can have a quantum spin of either 0 or 1. In most superconductors, it is 0. That change in spin has an absolutely dramatic effect. The universe is built out of 2 types of things, those with half-integer quantum spins, like electrons, and those with integer spins, like photons. Superconductors turn electrons into things more like photons that can travel through space forever. Cooper pairs can travel inside superconductors forever. This means that anything that pushes electrons, like a moving magnet, suddenly has a dramatic effect. The superconductor creates a magnetic image of any nearby magnet, just like a mirror makes an image of your face. Push the north pole of a magnet up towards a superconductor, and the superconductor creates the same north pole with electric currents. But like poles repel. That means superconductors always repel magnets. That was the story, so let's do it and see if it works. For this activity, I have a piece of yttrium barium copper oxide ceramic, and here I have some liquid nitrogen. Now I'm dipping this ceramic into liquid nitrogen to cool it to liquid nitrogen temperature, which is minus 200 degrees Celsius, making it a superconductor. Suddenly it can conduct an electric current without any resistance. I can hold the magnet over the superconductor. As you can see, it is now levitating. It floats because it has created a magnetic image of the magnet that always repels. So, in maglev trains, coils of superconducting wire are cooled to extreme temperatures, approximately 240 degrees below zero, to turn them into superconducting materials. Huge electric currents can flow through them without getting hot, allowing them to generate magnetic fields up to 10 times stronger than ordinary magnets. This is enough to hold up a train. These magnetic fields interact with simple metallic loops set into the maglev guideway. The loops are made of conductive materials like aluminium, and when a magnetic field moves past, it creates an electric current that generates another magnetic field. 3 types of loops are set into the guideways to do 3 important tasks. The first loop generates a magnetic field, causing the train to hover approximately 15 centimetres above the guideway. A second loop is responsible for maintaining the train's horizontal stability. Both loops utilise magnetic repulsion to ensure the train stays in the optimal position. If the train deviates from the centre or moves closer to the bottom of the guideway, magnetic resistance increases, correcting its position. The third set of loops utilise both magnetic attraction and repulsion to propel the train along the guideway. These trains can travel up to 600 km per hour. The ride is super smooth and there is no noise from wheels. But after the train has passed, the aluminium is hot. Energy has been wasted in heating the aluminium because it is not a superconductor. So maglev trains are not frictionless. If we could replace the aluminium with room temperature superconductor, then the only friction would be air resistance, and we could have maglev trains everywhere.